We've already learned about gravitational force, and we've also learned about electric force. Both of these exist in our everyday lives. Like every other force, electric forces have magnitude and direction, and we can analyze the magnitude and direction of electric and gravitational forces by drawing free body diagrams. Here we have three particles with different charges. The first one has a charge of negative 2q, the middle one is positive q, and the one on the far right is negative q. Remember, q is the variable we often use for charges. So this is just saying that the charge on the left has twice the magnitude of the other two charges, and it has the same direction or the same quality of charge as the one on the far right. The one in the middle has a different type of charge, positive versus negative. So if we were to draw this free body diagram, we would draw it so that the tail of each arrow, so we're going to draw a free body diagram of the forces on the center charge. So we put the tail of the arrow pointing toward the charge on the right. Okay, so the middle charge is attracted to the charge on the right because we have a positive and a negative charge. And the middle charge is also attracted to the charge on the left, but it's attracted with twice as much force, so twice the magnitude. So we draw a vector that is twice as long. So what's happening to this particle in the center is it's being pulled to the right and to the left, but it's being pulled to the left with twice as much force. And so the net force is going to be, if we add these two vectors together, the net force would be, let me change colors to represent net force. The net force would be to the left, and it would be with the same magnitude as the force to the right, or half the magnitude of the force to the left. You can do this with any charges. You can draw free body diagrams if there's a force, if there's a if there's another charged particle in the area, you can draw a free body diagram, and it might show a net charge, it might show no net charge, depending on what the forces add up to. I'm sorry, not net charge. It might show a net force, it might show no net force, depending on what the forces add up to. If the masses of the three particles were the same, then a free body diagram would look a little bit different. The center particle would have equal forces to the left and the right. It would have equal gravitational forces of attraction to the left and the right, because now we're looking at mass, not charge. So if the left mass were 2m, the gravitational free body diagram would have the same form as the free body diagram of electric force. So that would look like you would have 2m, m, and m. And of course, there's no negative mass, so the gravitational force would be the center object would be pulled to the right, and then it would be pulled to the left with twice the force. So if you double the mass, you have twice the force of gravity. If you double the charge, you have twice the force of twice the electric force. Let's look at this paragraph. Suppose you wish to keep a lightweight table tennis ball in the air, a ping pong ball in the air, by charging it and placing it 10 centimeters above an equally charged hoop. You want to make it levitate 10 centimeters above a hoop. If we treated both objects as if they were point charges, so we didn't have to consider mass, then the typical small hollow ball for table tennis, it has a mass of 2.7 grams, or 0.0027 kilograms. We write it in kilograms because We write it in kilograms because kilograms is the base SI unit. So its force due to gravity, I guess we are considering mass. Its force due to gravity is, we're not considering volume. Its force due to gravity is 0.026 newtons because 0.0027 kilograms times 9.8 meters per second squared comes out to 0.026 newtons. That's its weight. To make the table, so the Earth is pulling the ball down with a force of 0.026 newtons. To make the table tennis ball hover, the electric force must be equal to the weight of the ball and in the opposite direction. So if we use Coulomb's law and the fact that the charges are equal, the charge of the ball equals the charge of the hoop, then the equation for charge can be expressed as Q equals the square root of FR squared over K. And this comes from Coulomb's law, which says F equals Q1, F equals K times Q1, Q2 over R squared. Since Q is the same, then it would be F equals um, F equals K Q squared over R squared. So when we solve for that, we get an equation like what's written here. The magnitude of charge on the ball and the hoop should be 0.17 microcoulombs. Okay, we tend to use microcoulombs because a coulomb is a pretty huge amount of charge. Okay, so the magnitude of charge on the ball and the hoop should be 0.17 microcoulombs. We have different kinds of charges. We've been dealing a lot with what we call static electricity. That's where an object has an electric charge, but uh, but charges can also move. Okay, so where we see lightning or a spark, that's where the charge moves from one object to another. It can be very powerful, like lightning. It can be very small, like when you touch a doorknob. We can also charge objects. There's a process called powder coating by which painters will use charged paint droplets and then they will stick to a grounded object. And then they bake it and it becomes a very hard finish. They also do this with automotive paints. They use charged paint droplets because they're attracted to the car. Suppose you were using a small charged particle to map an electric field. The electric force is proportional to the particle's charge. If you release the particle, the electric force causes it to accelerate. Using Newton's second law of motion, F equals ma, remember that? You calculate the acceleration by dividing the electric force by the particle's mass. The acceleration is proportional to the particle's charge and inversely proportional to the particle's mass. So it should be the acceleration is directly proportional to charge and inversely proportional to mass. Let's look at these three statements about kinetic energy and potential energy. Statement A, a charged object has kinetic energy because of its position in an electric field. That is false. Okay, that is false. Charged object has potential energy because of its position in an electric field. Remember, potential energy has to do with position or orientation, and kinetic energy has to do with movement. So if two positively charged objects are pushed closer together, the system of the objects and fields gains potential energy. Okay, that is true. The system of the objects in their fields gains potential energy because they're positively charged. Two positively charged objects, when you push them closer together, they're going to want to repel each other. So they're going to be gaining potential energy. You have to add that potential energy to push them closer together. And C, when a charged particle is accelerated by an electric field along field lines, it loses potential energy and gains kinetic energy. Okay, we know that when an object is accelerated, or even when it changes position in a field, it is, if it's speeding up, it's gaining kinetic energy. So it's losing potential energy and gaining kinetic energy. And here we see an example you'll have to read about in your book about mass spectrometry. It's an object that can be used to determine the charge to mass ratios of very small particles. So the energy of the object in the gravitational or electric field can change between potential energy and kinetic energy, therefore changing that ratio. Potential energy should be associated with position. Kinetic energy is associated with motion. One last little fill in the blank. Mass spectrometers sort particles by their charge to mass ratio, or Q over M. Q is charge, M is mass. Q over M is charge to mass ratio. A particle with a charge Q and a mass M would end up in the same place as a particle with 2Q and 2M because the ratio is the same, right? Q over M equals 2Q over 2M. So the mass spectrometer is just determining the ratio. A mass spectrometer could not be used to distinguish between particles with 3Q and 1M and particles with 9Q and 3M because the ratio is the same. 3 over 1 is the same as 9 over 3. So the mass spectrometer can tell the difference between a particle with a ratio of 3 to 1 versus a particle with a ratio of 1 to 1, but it cannot distinguish between two particles with the same charge to mass ratio. We're going to stop with, or we're going to finish with a little video about uh, droplets. This is on the International Space Station, and we're going to see an example, a real life example here.
What you're looking at is a knitting needle, and I happen to have in my crew preference a couple of knitting needles. And not that we have a lot of time to do knitting up here, but there's some other neat things you could do with them. So here I have a piece of paper, and I rub the knitting needle with a piece of paper. And now I'm going to take a syringe with a little Teflon cannula. I'm going to squirt drops of water out, and look what happens when those drops of water get close to that charged knitting needle.
Okay, so he has some charged drops of water near a knitting needle. This is in zero gravity. So gravity is not a factor here, only charge. Look at how the charged particles, the charged water particles, react to that knitting needle. They kind of orbit it, right? They're attracted to it, and they move around it.
So this is like a little satellite going around a cylindrical shaped planet. Except the physics here is a little bit different. It's not about gravitation. It's about charge forces. And of course, charges can exert a potential field, as we call it. So it can exert a force at a distance with no tangible connection. And so you have a charged drop that was ejected from the Teflon tipped syringe. And then you have the charged knitting needle, and they're going to be attracted if they're opposite charges. But because the drop has some velocity to it, it's orbiting around the knitting needle.
So the charge acts like gravity.
To be a little different than when we started out. This knitting needle is made out of Teflon. And Teflon has some really neat static charging properties when you rub it. And I figured it'd be good to have a Teflon knitting needle when you're on station. Here we have some little tiny droplets. They kind of remind me of flies on a picnic out in Houston. And these droplets, the bigger ones that you're seeing there, are about 6 to 7 millimeters. That Teflon rod is about 6.5 millimeters in diameter. And then here you see a bunch of little tiny droplets, and they're making spirals. They go down the cylinder for a while, and then they'll reverse their direction and spiral back. Now, if you look closely up in the upper right-hand corner, you'll see the injection nozzle from the syringe, but you also see that I have a second knitting needle. And that knitting needle is made out of nylon. And so you can rub the nylon, you can rub the Teflon, and there's some interesting charge properties that happen between Teflon and nylon. And I found that it's useful to have these when you want to put a charge on a droplet so it will orbit your knitting needle. And of course, once you set up a knit needle like this, you start to play with the water droplets. You just can't have too much video like this. It's so much fun to watch these little droplets and notice that they get closer and closer to the knit needle. Their orbits go faster and faster, and the further away from the knit needle, the slower the orbit. The closer to the knit needle, the faster the orbit, and that's the same thing with orbital mechanics when you have a satellite around a planet. And again, the physics is different. A satellite's orbiting planets is gravitational potentials and gravitational forces, and this is static electric potentials and static electric forces. It's an analogous rationale to why we do surface tension experiments up here. Surface tension is a very weak force, and gravity overpowers it. And when you go in a weightless environment, you effectively remove the gravitational forces, and now you can look at unadulterated surface tension physics. I'd like to leave now with a question for students or anyone else that might be watching this. And that's to try to figure out, why do I have a Teflon knit needle and why do I have a nylon knit needle, and, and why I use the knit needles the way I did.
Well, that was just way cool, Don. We were really enjoying that.